Alright, so in this video we're going to be looking at RStudio again, specifically doing some probability related topics, largely related to Bayes' theorem or Bayes' rule, right? And so we're going to be doing some things like creating some contingency tables, showing how you can do that in a manual way. We're also going to be looking at calculating expected values for a discrete distribution, and then also showing how you can update prior beliefs using Bayes' theorem with just a few commands here in R. Okay, now before we get into this, there is one thing that I want to do first. Right? So if you've watched my previous videos about doing these kind of labs, I've been using R script. Right, so that is one option for a way that you can code your R. You can code your R language work. Now, another option that is in RStudio is what they call an R Markdown file. Right, so it has the extension RMD. Now, this has a few benefits over the standard R script, which is just a .r file. Right, so it can do really three things. Right, so one, you can actually store the output in the RMD file itself, right? So whenever I open an R file, I have to run it again to see what kind of output you created. And this might actually lead to variances in output, especially if there's any kind of randomization that happens, right? So if you use, for example, the sample function, right, that is something that will be different every time you run it, right? In this case, though, you can just store the output, and then I can see exactly what was created. A second thing is that you can include large blocks of additional text that are not code without having to use the comment kind of symbols, right? So that's another option, or another benefit. And finally, you can knit your, knit is the term they use for exporting your results in some other type of file. So something like a Word file, a PDF, an HTML, or even something like a PowerPoint presentation, right? So all of these are things that you can do, right, using an R Markdown file relatively easily. So I'm going to go ahead. This time we are going to work with an R Markdown file. So to show how to create that, the first thing, fairly straightforward. If you go up to the File menu, right, and then choose New File, you can't see this all on my recording, but you'll see it if you're in RStudio. There's the option R Markdown. It's the fourth option available, at least in my version of RStudio. So when you click R Markdown, you get this dialog box. So this is asking for some information related to this Markdown file. So the first thing I want to do is give it a title, and for my case, this is going to be Lab 3, because this is the third lab video I'm doing. Author, Prof E, that's me. The date, I'm just having, this is the date that I'm doing the recording, so that's fine. And then finally, the default output format. Now, I will say you are not heavily committed on this. You can easily change this if you want to export as a different type of output. So I'm just going to go with HTML. It's simple enough. All right, so I'll go ahead and click OK, and that will create this document. And there we are. Now, you may have noticed there were some other options when you go into R Markdown. Let me just open that back up for a second just so you can see some of the other options. Over here to the left, you can change the type of exporting you're doing. So you can see I'm exporting as a document. So that's really good if you want to export into Word or as a PDF and have it kind of that page setup. If you do this presentation, you can see you can have this as HTML slides or PDF. There's a program called Beamer, which allows you to create PDF slides. And it's a very common thing for academic presentations to use Beamer. And then naturally, PowerPoint is fairly familiar. Right? So all of these are options as well if that's what you need. But I don't, so I'm going to cancel out there. Right, let's go ahead and take a look at this. Now, for our purposes here today, I'm really not going to need this console window because remember, all the output's going to appear inside the R Markdown file. So I'm just going to go ahead and shrink that down. Like I can always grow it back up if I need to, but there it is. The console is just relegated to the bottom. So what we have here, you can see all the preliminary stuff in the first few lines. Right? Then this set of code is what we call a chunk. Right? You can see it's for setup purposes. And what it's doing, it has some options here. So one you can see is include false. What that means, right, is that if you knit this into a Word document or HTML or whatever, then this is not going to be included as part of that. However, it will run. It's still going to run. It's just not going to appear in whatever your that type of file is. Okay. Another point about this, so the way that you tell an R Markdown file that it's dealing with code, right, is that you use these three tildes. That's the upper left corner. It's not tilde. It's I guess it's the accent grave, I think, or something like that, right? So it's the single quote, but kind of slanted that you have in the upper left of your keyboard. Okay, right. So right there, so you have that followed by a brace, and then and then R, right? And that indicates there's R code coming, right? Then we can follow this with a descriptor for whatever that chunk would be named. So setup would work. So you can see down here, this is describing this as chunk 1, so it's the first chunk of code that is recognized, and it is named setup. Yeah, and then you would have your code in here, and then you finish again with these 3 accents. Right? Then you can run this code if you wish using the play button right here. Right? That allows you just to run whatever that particular chunk happens to have in it. You can also control the options if you wish. Right? So that allows you to bring up things like, oh, should you show the code and output or not? Right? Or there are other options like you can show output only or show nothing. Right? So show nothing would be include false right there. All right, but I'm just going to go with whatever it originally had. Here we go. All right, apply. All right, and that is that. Okay, so now you can see right here, all of this code here that is not inside a chunk, that is just treated as a comment, right? So none of this is going to try to run as code. You're not going to get a bunch of errors for lines 11 through 17 here because R recognizes that this is not, in fact, something that you are wanting to run. Right. Then we have another chunk of code here, which is going to run a little bit of R code. Then we have, again, more comments, and then some more R code, and then some more comments. Right. So that's the way things are set up. So I'm going to start with this file, and then we're going to modify it. I want to keep the setup here the same. I'm going to type a little bit here just to do some setup for us as we get into doing the first task, which is going to be creating a contingency table. So we'll type that just for some notes is the idea. Okay. All right. So that's my goal there. Another point is that if you are importing data, then just using the import dialog box, which we've used before, right? So you have this dialog box here. That by itself will not be sufficient. If you decide you want to knit as some output that is outside of RStudio. In that case, what you'd need to do is also copy this code here, which you can copy here, right, to the clipboard, right? Then you can close this out, and then you can paste it in here if you wish. So I could, for example, right here, just a simple Control V right there. Right, so I could use that if I wanted to read in any particular file. Okay. All right, so just so you know, if you're using some kind of data set that you're importing, you do need to have that code inside of an RMD file, right, so the markdown file. All right, so let's get into our task. We're actually not using a data set this time. Instead, everything we're producing is going to be inside of R. We're going to use R to do some calculations for us, and that will create the data that we want. Okay. All right, so first thing, let's make and use a contingency table. Right, so the idea of a contingency table is that it allows us to think about various possible cases. Right, so I'm going to go ahead and delete some of this, some of these notes here. All right, so I'm just going to note here about a contingency table. So our goal with this contingency table is that we want to create a table, right, which is going to divide up 1,000 people. This is 1,000 people. Of these people, 10% of them, right, have a particular disease. You pick whatever disease you want. There, 10% of people have this disease, so it's a reasonably common one, right? Okay, but it's one that you would generally get testing for. We're going to make that assumption. Now, if you go and get testing, right, then the test, we would say, is very sensitive. That means that if you have the disease, you're very likely to test positive. Specifically, 99% of those with the disease will test positive for it. So if you have the disease, 99% chance you're going to get a positive test result that is indicating, yes, you do have the disease. But this particular test, while it's very sensitive, it's also not very specific, which means you get lots of false positives. Now, it's not like 90%, but let's say there are 20% false positives for those that do not have the disease. So that is 20% of those without the disease still test positive. Okay, so that's what we know. Now what I want to do is create a table, just a 2x2 table, which describes the 4 possible groups of people. Right, so how I want this to be set up, so just to give a sense of that. So we're going to have those that test positive in one column, those that test negative in another column. Right? Then we'll have as well right? So our two rows will be those that have the disease. Yeah, maybe need a little bit more space there. And those that don't have the disease. There, that works. So when we divide this up, we'd have these four groups. So one set of people test positive and have the disease. So these would be the true positives. I'm just going to call that true pos. Right? But some people have the disease but test negative. This would be the false negatives. Right? And the next row, we'll have the false positives. That is, those people that don't have the disease but still test positive. And then the true negatives, the people that don't have the disease and test negative for it. Okay, so these would be the four groups. Now what we need to do is calculate how many people are in each of these groups. And that's what I'm going to have R do for me. So there's our contingency table, is what I'm going to call this. Right, so it's just renaming what this chunk is called. I do not need a summary of the cars variables. Okay. Instead, what I need to do is do some math. Right, so the first thing I'm going to do is calculate the number of true positives. So true positives, right, I'm going to assign, this is just assigning a value, right, to this variable that I'm calling true pos. So to find the number of true positives, what I need to know is what percentage of people who have the disease test positive for it, what percentage of people have the disease, and then the number of people there are. Right. So this would be a case of the multiplication rule, where we take probability of A given B times the probability of B, and then we're just multiplying by the size of the population we're dealing with. Okay, so in this case, we need first, if you have the disease, right, what's the probability you test positive? Well, there we know that's 99%, so 0.99. Now we'll multiply that using just an asterisk for that. Multiply that by the percentage of people that have the disease. That's 10%. So that's the multiplication rule at work there. Multiply that then by 1,000 to get the number of people. Now a similar calculation for the false negatives. So the false negatives, right, so these would be the people that do have the disease but test negative for it. Right, so we know if you have the disease, there's only a 1% chance of testing negative, because 99% chance you test positive, so it's just the other side of that. Right? And we know 10% of people have the disease. So once I eliminate my typos, right, so it's 0.01 times 0.1 times 1,000. So 10% of people have the disease. Of those, 1% will test negative. Right? Next, then I want the false positives. So my false positives, these would be that 20% of those that don't have the disease. So 20% times 90%, because 90% don't have the disease. Multiply that by 1,000 to get the right number of people. And then finally, oh, it's a false positive, and then we need the true negatives. And that would be the 80%. Like, if you don't have the disease, 20% chance you test positive, 80% chance you test negative. So 80%, 0.8 times 0.9 times 1,000. Not 100, 1,000. Okay. All right, so those are the calculations that we're going to do, and that should tell us how many people fit into each of these four groups. Now our goal is to have this all appear as a table like you have here in the middle of the script window here, but we're not quite to that point. Okay. Just to make sure that I didn't make any math errors, all these should add up to 1,000, so I'm just going to do that math real quick. So true pos plus false neg plus false pos plus true neg. There we go. And then we can hit the play button to run this, and then it's going to do the math for this last line, and it adds up to 1,000. Excellent. We want to make sure that it adds up to 1,000 because there are 1,000 people. Everybody fits in one of these four groups, and only one of these four groups. This works. Perfect. Okay. All right, so I don't need that line anymore because knowing that there are 1,000 people, I was just using that to check my math, honestly. Now to create the table, I'm going to use the matrix command. Now the format of the matrix command, we can actually see by going matrix here and just selecting it. So you can see first thing we need to do is put the data in. Then we need to tell it the number of rows, the number of columns. Tell it whether we're putting the data in by row or by column. So it's just by row false means we're putting it in by column. And then dim names that tells R what do we want to name the various lines, so the rows and the columns. Okay. All right, so let's go through that. So for our data, first thing we will do is put that in. So in this case, we're using the concatenate function. It's just a C. Right? And then inside that, we're going to put the data in. We're going to read it by rows. Right? So looking at the table above, we know it's true pos, followed by false neg, followed by false pos, followed by true neg. There we go. So we have all the data in there. Next thing I want to do is to find the number of rows. So it's n row equals, there will be 2, and n col equals 2. Right? 2 rows, 2 columns. It's a 2 by 2, so just 4 elements inside there. This time I am putting things in by row, so I read across the rows rather than down the columns. So by row is going to be equal, not by row equals true. All caps, that indicates that yes, this is what we're trying to do here. The last thing I need are my names for my dimensions. So dim names, just put an equal sign there. What I need to do here, it's actually a list of names. So type in list, like so. And then we're going to use 2 concatenate functions. So the first one, so C, parentheses again, and now we're going to put in the names we're going to use for the rows. So I'm going to use have the disease, put this in parentheses, and not in parentheses, put this in quotation marks to indicate I want this to appear as this specific text, right? Then comma, and does not have the disease. Okay, then that ends that particular concatenate function. And then we need another one. It's another C, and this will have the names of the columns. So we want to test positive and test negative. And then end that. Okay, so this would create the matrix. So I'm going to go ahead and run this just to show the matrix creates properly. Yep, there it does. And it shows just the way I would like it to. Now, but I don't want just to look at the matrix like this. I want to store it and then make some modifications to it because I want to use this to do math, right? So in order to store it, I'm going to put a name here to the left. I'm just going to call this disease table and then use the assignment operator. So make that little arrow with a less than sign and a minus. Okay. All right, so that will save this now as disease table. And then from this point, if I want to look at the table, all I have to do is use the print command. So print disease table. This then will display it to the screen in the console and also put it inside of the R Markdown file. Okay. Another thing you can do, just while I'm on it, in an R Markdown file, this X here allows you to clear whatever output you have. So if I don't want to include this, I can just hit the X. And there, now that output went away. So it'd have to be recreated if I want it again. Okay. Right, so we do have this table here. Let's go ahead and bring it back. There it is. Right, so this is what we have. So what do we want to do with it? So we know of this 1,000 people, 99 have the disease and test positive, 180 don't have the disease but still test positive. So we have all of these groups. What I'd like to do, though, is use these to come up with some other probabilities. So there are 2 sets of probabilities that I want. Right? So one of them would be I'd like to know in each row, right, given that you're in that row, what is the probability of being in that column? So put another way, given that you have the disease, what's the probability you test positive? What's the probability you test negative? So in order to find this, what you need to do is use a simple command. It's disease table. Divide that by row sums. And then the name of the table here as well. Right? So what I've done here, I've taken the name of the matrix, disease table, and then I divide by row sums, disease table. So what this will do, it will go through and it will sum up each row, right, and then divide that row, right, by that sum. So in this case, it will go through the first row, it'll take 99 plus 1, that's 100, and then we'll divide through that entire row by 100. Right? Take the second row, 180 plus 720, that gives us 900, divide that row by 900. So let's go ahead and see what that looks like. So right there's our first one, and then here's our second table right there. And we can see that we have 99% here, 1% there, 20%, and 80%. Those numbers should feel familiar, because those are what we use to build the table. So we know if you have the disease, 99% chance you'll test positive. You don't have the disease, 20% chance you'll test positive. So this is really just feeding us back that we previously created. Now what might be more useful to us is knowing the opposite. That is, if I test positive, what's the probability I have the disease? Now, intuition, we might think, oh, it must be 99%. But that's not really accurate. In fact, we know it's not accurate because when we look at the numbers, we see if I test positive, 99 of those people have the disease, 180 don't. So it's actually less likely that I have the disease than that I don't have the disease if I test positive, because there are more people that fall into the not having the disease category amongst those that test positive. But I want to get more precise with that. So to do this, I need another line that looks kind of like line 30, but if I try to run it the way that I ran line 30, it's not going to work. So here, let's go ahead and do that first. So warning, this is not correct. This is not going to work. But I do want us to see what the problem is, so then we can talk about how to fix it. All right, so this is disease table divided by call sums disease table. This feels like it should work, right? So if I can do row sums, well, what I want to do here is take the column sum, so 99 plus 180, divide the column by that, and we're good to go. The problem is that this divide function, whenever you're using it this way, it always divides the first row by the first thing that you have, and the second row by the second thing you have. So what I'm going to get here when I run this is not 99 divided by 279 in that first cell, and then the cell underneath it having 180 divided by 279. Instead, what I'll get is 99 divided by 279. Right, from here, then we'll start reading across the row and do 1 divided by 279, which is not what I wanted to do. So I'm going to have to modify this a little bit. Another way you can tell this is here if I run this, I'm just going to go ahead and run it to make this point. Okay. All right, so this last thing I came up with, we should end up with the cell here and the cell here, right, adding up to 1, because if you test positive, you must either have the disease or not. Instead, this adds up to roughly 60%. Clearly, it's not doing what I want it to do. Okay, so how do we fix this? Well, what we need to do then, because we know it's going to go across rows, we need to convince it to use that what was a column is actually a row, and there's an easy way to do that. There's the T function. What T does, it transposes a matrix, which means it takes all the rows and columns and flips them. Right. So what was a row, it now reads as a column. What was a column, it now reads as a row. Right, so if I run it like this, let's see what that does. Okay, it's down here. You can see it flipped it, right? So now we have test positive is reading across, test negative is reading across, and we are getting reasonable answers, right? So 35% of those that test positive have the disease, 64.5 roughly percent of those that test positive do not have the disease. Nice. The problem is I don't want it to display this way. I want have the disease, do not have the disease to be the rows, not the columns. So I can fix that by adding another T function, right, to the outside of all this. Right, so first thing I did, if we read this, is that we flipped the disease table, switching the columns and rows, right? Took the column sums, right? Divided the rows in the disease, well, what was the row in the disease table, what was the column is now the row in the disease table by those column sums, right? And then flip it all back, right? So that's the goal. And let's see if it runs properly. Is this last one here? Yes, perfect. So all of them have that test positive, test negative being the columns, but now we have things correct here, in that this would be if you test positive, what's the probability you have the disease versus not? If you test negative, what's the probability you have the disease versus not? Beautiful. Okay. All right, so we got this all there. And then you can use this type of table to calculate all kinds of things, right? So we've got if you test positive, what's the probability you actually have the disease? We can read off from this. If you test negative, that just puts us in the second column. What's the probability that you actually don't have the disease? We can read that off to get some sense of how confident we should feel about any test result. Another thing we can do, now this one would require looking at the overall numbers up here, right? We can find the overall level of accuracy, right? So how many of these tests are actually accurate? And then we can calculate that as a percentage of the 1,000 total. It's all of this is stuff that we can do with simple calculations here in R, and then we can create these tables without too much problem. Okay. All right, so let's go ahead and take another look at something else we can do. I'm not interested in plots here. Instead, what I want to do is talk about expected value. Right, so the idea of expected value, right? Expected value is basically like an average or a mean, right? Except that it's weighted by probability instead of the number of instances that shows up. Right, so you can really think of this as, right, whatever the probability is the number of times that a particular observation shows up. So let's say that we have a particular case, right, and I have a table here describing this. If you have the instructions for my lab, if you don't, you're somebody watching on YouTube, well, I apologize. So feel free to write this down. Right, so we have, suppose I'm looking at two different investments, investment A and investment B, and they have different return structures. Right, so in the case that the economy is doing superb, let's say that happens about 20% of the time, both of these investments, A and B, return 30%. On the other hand, if the state of the market is just great instead of superb, let's say that happens 25% of the time, investment A returns a little bit less. Let's say it's 20 versus the 30% for B. If the market's good, right, let's say that's another 25% of the time. In that case, investment A returns 15%, investment B still returns 30%. Now, so what we've got here for investment B is that it returns really, really well as long as the market is good or better, right? However, then things change, right? So when the market's just average, say that happens 15% of the time, then investment A returns 10%, while investment B returns nothing. A mediocre market, which happens 10% of the time, say, they both return nothing. It's just break even. If the market is poor, which is fairly rare, let's say it's 5% of the time, then investment A returns negative 20%, so you lose 20%, where investment B, you lose everything. As you have a 5% chance of losing absolutely everything with investment B. So what expected value does then is allows us to take these different numbers for the returns and average them in a weighted way, right? So it takes account of the fact that, yes, this poor result is, say, really bad for investment B, but it also doesn't happen very often, right? So that's what we can do here, right? So that is the goal, right? So it's really looking for, in effect, a weighted mean. Is what we're looking for. That is, we're weighted by probability of occurring. Right, so for this one, let's turn off the echo false. I do want this actually to appear. So R, we're going to do EV, right, for expected value. Right, so what I need here, right, I'm going to use a very simple function called weighted.mean. Right, now for this, you need two things to go into it. One is the data values, and secondly are the weights. So I'm actually going to put the weights in first. So the weights in our case would be the various probabilities of the various states of the market. So we have a 20% chance of superb, 25% of great, 25% of good, 15% of average, 10% of mediocre, and 5% of poor. Right. So using the concatenate function here, right, to create this list. Next thing I want to do is put in the returns for A. So A return is what I'm going to call this. And then we need to put in order, right, the various returns. Remember, so it was 30 at best, then 20, 15, 10, 0, and negative 20. And then do the same thing for B. So C for creating the list. And remember, it's a 30% return in the first three states of the market. Then it just breaks even in the next two, and then you would lose absolutely everything in the last one. Okay. So I've got all the things that I need here. I have the values for both investment A and A return, and B return. And I have the weights, that is, the probability of each possible observation happening. Okay. So then how do I use this function? Pretty straightforward. That is, it is weighted dot mean. Okay. And then I just need to put in A return. Right, that would give us the returns for A. And then WT for weight. And then I can do the same thing, so using the same line, but now B return, and the same weights. Okay. So when I run this chunk, what it's going to do, right, is create these weights and these returns, both for A and for B, and then it will calculate what is the weighted mean for each of these investments. Okay, let's go ahead and run it. We see that investment A returns, on average, 15.25%, so that is, once you take into account the probabilities involved, 15.25 is about right. And then investment B returns a little bit more, at 16% on average. Okay. Now, another thing we might be interested in, though, is not just the weighted mean, but also the weighted median. There is also a function for that, but it is not in the basic install of R. You have to install a separate package. So we're going to go and get that package. It's called SPATStat, I believe. Yes, SPATStat is correct. Just had to check my notes. So I'm going to install here. All right. So we're going to install the package SPATStat install. Okay, and then the console here starts the install process. It takes a little bit to run through all of this. Make sure everything unpacks correctly. There we go. We're all good. All right. So now we have that installed. Right. And we can come here. And remember, we need to load that library. So we'll do library, SPATStat. Yep, just SPATStat here. And then weighted median. A return dot weight, not dot weight, comma weight, WT. And then weighted median for B return. Weight. And then we can go ahead and run that. And we can see that returns here. Oh, they had to load a bunch of required packages. All right. We've got 15.25 versus 16, which we had before. Down here we have 15 versus 30, right? So in terms of median, right, it looks like the median is significantly higher for investment B than investment A, right? Meanwhile, investment B has only a slightly higher mean. Now this is just reflecting the fact that most of the time, in fact, if you add up these weights, it ends up being 70% of the time, I believe, investment B is going to return 30%. Right? But when it doesn't return 30%, things get really, really bad. So you lose all of your money 5% of the time. So that drags the mean down quite a bit, even if the median indicates that that is not a typical result. Right? So this would be a case of what I've heard described by Nassim Taleb likes to talk about this, of a fat left tail. That is where you have a relatively small probability of a negative result, but the negative result tends to be very, very bad when it happens. Okay, so this would be that type of investment. Okay. All right. So those would be the functions you can use here to answer those kinds of questions, like what the expected value is, but also what the median would be in this kind of weighted way. And now noticeably, if you only looked at this list of numbers here and took the median, it's an even number of numbers. We'd look at the two center ones and go halfway between. It looks like it would be 15, which wouldn't be that different, right? However, remembering that each of these 30s is in fact not equally weighted with these zeros in this negative 100, right, tips the median right in their direction. Right? So that's why we have to do the weighted thing. Okay? It's really kind of like, right, imagine that we have, say, a list of 20 30s, then 25 30s, then 25 more 30s, then only 15 zeros, then 10 more zeros, then 5 minus 100s. So we'll give each percentage point one observation. Right? In that case, the median would very clearly, right, be 30. So it's another way of thinking of this. You could also use that method to think about how the weighted mean works. Right? And that, yeah, this 30 is not just one 30. In fact, it's 20 30s, one for each percentage point being thrown in. All right, I'm going to need one more chunk here. Right. So the last thing we want to do is update prior beliefs using Bayes' theorem. So this is something where like the setup is kind of odd, right? But working things out inside of R is remarkably easy here, it turns out. Okay, so this is what we're going to do. Right, so first, just as a reminder about what kind of Bayes' theorem tells us. At the core, Bayes' theorem suggests that the probability of B given A is equal to the probability of A given B times the probability of B divided by the probability of A. And then you can plug any other A's and B's you want in here. We could, in fact, have used this, right, to answer questions like what is the probability of, say, actually having the disease if you test positive for it way back in the first big task we did, right? So you can use this formula there. As long as you can compute all of the elements on the right-hand side, you can find what the left-hand side would be. Now, there is a particular kind of philosophy of science that adopts this Bayesian kind of approach, which would say, well, let's make B the theories that we're looking at and A the data that we look at. So putting these in, this tells us the probability of a particular theory being true, given the data we observe, is equal to the probability of seeing that data given that the theory is true, right? Times the probability we assign to that theory being true, this is what we call the prior probability, divided by the probability of that data being observed. Okay, so it's really just plugging in theory for B and data for A, right? But this has rather profound abilities for us to tell us how we should change our mind, right, as we approach new data. So I'm going to do a rather silly case, right? So let's suppose that I have a bag of dice. Okay, I do actually have a bag of dice. I keep it on my desk in my office, and I also have more dice at home. That's what happens when you play role-playing games. You have lots of dice, right? Right. So, and I have them. They have different sides. Right? So, one is a four-sided die, and it's numbered from 1 to 4. A standard six-sided die numbered 1 to 6, an 8-sided die with 1 to 8, 10-sided die with 1 to 10, 12-sided die 1 to 12, and a 20-sided die 1 to 20. So I have these 6 different dice that we're looking at. Now let's just say for the scenario that I pull one of these dice out of my bag randomly, Right? I don't show it to you. I just roll it and tell you what the result is. Right? So I roll it and I say it's a 10. Now I want you to try to figure out what is the probability of me having rolled each possible type of die. Right? So put another way, right? We could say probability theory given data. Let's rephrase that. This probability of this particular die given rolling a 10 is equal to what's the probability of rolling a 10 given this particular die, if I can type, times the prior probability that you attached to this die being chosen, divided by the overall probability of rolling a 10. That's what we're looking for here. So let's go ahead. I'm going to create another chunk of code here. So remember, we need the 3 accents there, and then R inside of braces. Does it? Okay, it doesn't actually provide the line to get out of this. So R, and I'm just going to call this Bayesian Updating. Okay, and then I'm going to create the 3 tilde line to close things out. All right, so here's my other chunk of code for my Bayesian Updating. Right, so what I need here, right, I need a few elements, right, to go into this. Right, one thing I'm going to need is, right, what are the prior probabilities that I attach to each die? I'm going to also need to know what is the probability of each die rolling a 10. Well, it turns out that the probability of rolling a 10 overall, what I need to do is take this multiplication we have in the numerator, right, do it for every single die, add them up, that tells me overall what is the probability of rolling a 10. So I can find this based on the previous calculations, just have to do some summing. Okay, so these are the elements that are going to come together. All right, so let's go ahead and do this. So the first thing I want to do, I want to define what my priors are. So priors would be what are my beliefs about each die being chosen before I see any data at all. Now I'm going to make the assumption that each die was equally likely. That is, we know there are 6 different dice. Each of them had a 1/6 chance. So I did 1 divided by 6 over 1, comma 1 divided by 6, comma 1 divided by 6, and so on. So those are my priors. Right? The next thing I need are my conditionals. The conditionals tell me, that is, what is the probability of rolling a 10 in this case, right, on this particular die. So I'm just looking at this element right here. Right. So let's go ahead and do that. So the first die we're going to deal with is the 4-sided die. Now I know if I have a 4-sided die, it only goes up to 4. There's no way I can roll a 10 on it, so 0. Same is true for a 6 and an 8-sided die. Now a 10-sided die has a 10 on it. It's on one face out of the 10. So 1 divided by 10. So the 10-sided die has a 1/10 chance of showing me a 10. Now the 12-sided die also has a 10 on it, but it's 1 out of 12 sides, so it's a 1/12 chance. The 20-sided die also, it has a 10 on it, but it's only 1 out of the 20 sides. So those are my conditionals. Now I need to kind of flesh out the rest. Right, so we know one of the things that I have to do is multiply the two together to come up with what my numerators are going to be. So I'm just going to call this multiplied, like so. I'm just going to take priors multiplied by conditionals. Now the way that R deals with this, so we have 2 different lists of numbers in effect, is that it multiplies element by element. So it'll take, so the first element here, I'm going to have, again, a list of 6. It'll be 1/6 times 0, then another 1/6 times 0, then another 1/6 times 0, then another 1/6 times 1/10, then 1/6 times 1/12, and 1/6 times 1/20. Right, so that is the way that it's going to do this calculation. Right, so if you, say, take matrix algebra or something like that, you know that if you multiply vectors particular ways, right, this would not really match some of that. Right, so it's just an element by element multiplication is how this works in R. Okay. All right. So that's going to tell me the multiplication of these two, right? So if I read out what multiplied says, that is the probability of that die being chosen and then rolling a 10 on it. Okay. Right, so it's that joint multiplication rule kind of probability. Now if I want to know overall, right, what is the probability of rolling a 10, I need to sum all of that up. So sum multiplied, right? That adds together all of the different dice that could possibly have rolled a 10, combined with the probability of them rolling a 10. So we can actually run this now to tell me what is the probability of me rolling a 10 here. Well, there it is. Right? So before you see anything, you say, I think there's basically a 3.89% chance that you're going to roll a 10, Professor. All right, so there that is. Now, to apply Bayes' theorem to get what are my posterior beliefs about where we end up. So, okay, now that I've seen this 10, right, that's new data, right, how does that affect my beliefs about what die was chosen? Right, so let's go ahead and do that. So it's posteriors. And this is going to be, just take the multiplied, right? That would be that probability of data times theory times the probability of the theory, which we had already calculated in line 59. And then we just divide that by the sum of multiplied. Since sum of multiplied is a single number, it's going to take everything in that list of multiplied and divide it by that single number. Okay. All right, so that's what it's going to do to create the posteriors. Now I want to actually be able to see it, so I'm going to create a nice table using the matrix function. Right, so we have BT table. That's Bayes' theorem table is what that stands for. You can call it whatever you want. Okay. I'm going to use the matrix function. Right, so first the data that goes into it, I need my priors and my posteriors. The number of rows here, it's going to be 6 rows, but 2 columns. Right, so we have 6 rows, 1 for each theory. Right, and then in this case, I am actually going by column. So when I list priors, I want priors to be listed in a column, not in a row. So it says that by nature, it's going to do false for by row, so it's reading in by columns. So I don't actually have to put by row in here at all. Right, so then I'm just going to put in dim names to get that in there, equals, and again, we use list. So first we do the list for the rows, right? So using the C function, so I'm just going to go one at a time. So it's 4-sided is the first one, then 6-sided, then 8-sided, then 10-sided, then 12-sided, and then 20-sided. If you're somebody that plays Dungeons and Dragons or something like that, feel free to use D4, D6, D8, D10, D12, D20. That works fine too. I know what that means. All right, so that's the list for our rows, and the columns are just going to be priors. So what were our beliefs originally, and then posteriors, telling what are our beliefs after we see that a 10 was rolled, or at least hear that a 10 was rolled, assuming you believe me. All right, so that's going to sum all of that up. And then finally, we're going to print that table, and we can see what things look like. And there we have it. Right, so we have our priors, right, so everything was equally likely before. Posteriors, now we know that neither the 4, 6, and 8-sided were all impossible, because there's no way you can roll a 10 on those, and we know a 10 was rolled. And these are our new probabilities for the remaining dice. Now this is just reflecting the fact that if I would know that I rolled a 10, right, that's going to be most likely to happen on the die. So it means most likely I rolled a die where it's most likely to happen that I roll a 10. Since the 10 is 1 out of 10 on a 10-sided die, but only 1 out of 20 on a 20-sided die, that means now we slant more toward believing it's probably 10-sided as opposed to 20-sided. Now, naturally, if I roll the die again and then I tell you, oh, I got a 14, that would narrow this down differently, right? So you can do the same thing again. It's actually not that hard, right? From this point, for you to update it again, right? So you could do something like, well, I know these are what my posteriors were after one roll. Well, what if I roll and get a 10 again, right? What does that do, right? And I can update it again, just like I did using the process up here. Right, so now instead of priors, I guess I can just redefine it. So I can just call it priors 2, right? Feed my posteriors into that, and then run through the calculation again to come up with a new set of posteriors. Right? So that is something that you can do here. Similarly, you could, right, using the same kind of calculation we did here, from multiplied, from priors times conditional, sum of multiplied, stick posteriors in here, and then we can say, okay, what's the probability that the next roll is going to be a 10? Well, we've updated our beliefs, so replace the priors with the posteriors, and then we have a different sense of what that probability is going to be. Okay, right. So I think that sums up the things that we can do here. Now, just so you can kind of know how this works, and I can show how this works. Right. So suppose then that I wanted to take this and rather than just have it as an RMD file, right, I would in fact like to knit it into an HTML file. Nice benefit to this is that the person doesn't have to have R for them to be able to see your output in your code this way. So in that case, what I want to do is knit. So if I click on knit, since I chose default as an HTML, it would create an HTML document. Or I can hit the little options here, right, in the whatever you call that little V triangle kind of thing. And that gives me the options for HTML, PDF, and Word here since I'm dealing with the document. Okay, so I can pick whatever I want. I'm just going to stick with the HTML. Right? So when I click knit there, the first thing it's going to do is require me to save my RMD file. So I'm just going to go ahead and save that. I'll save it on my desktop, I suppose. I'm going to call it lab3. Okay. Now, notably, you can just save the RMD file and submit that to somebody. As long as they have RStudio, they can read the RMD file, and it will still include all of the output. Right, so save there. All right. And now after it saves, it can knit, maybe. All right. Right, so it knit, and let me show you what that looks like in my browser here. So I need to switch over to my browser window just so you can see the display. So give me just a second here to swap windows. There it is. Okay, so this is what it looks like inside of my browser window. Right. So you can see here it has the name of the project, date, and name of me, right? And then it has all of this explanatory text. Now, one thing you might notice is that because I didn't have multiple rows between these lines, it just kind of put everything on one line. So you'll have to get used to kind of playing around with that, right? All right, and then here we have. I'm not sure why that's there. I'll have to go back and double check this. Okay. Right. Oh, okay. This is trying to display what that table is supposed to look like. Apparently it decided to read some of that kind of oddly here, probably because it started with a bunch of tabs in that line. That's probably what threw that a bit. Okay. Then we have all of the code here, and then the output from that code, code and output from the code, code and output from the code. Okay. And then does the same thing here. So there's the code, output from the code, code, output from the code. Right. In this case, it loaded this library, gave me the output from that, and so on. Right. So in each case, we can then see what output came from which code. Right. So that's kind of a nice way for you to share your results right with somebody else. All right. And I think that I may not have been showing you. I think I did. Forgot did. Okay. So let me show you now. Okay. All right. So we have the title and name, date, and then here you can see where things didn't quite break up like I might have expected. I think it might be one of those things where you have to have multiple lines to get it to give to have a line break, or just breaking to the next line is not sufficient. And this is where I was saying that I think that some of the tabbing went weird or something like that. All right, so there would be some things here that I would naturally want to change if I wanted this to look nice. I'm not particularly worried about it for this case. It's just for demonstration purposes. And there you can see the code, right, all with kind of the light gray background behind it, and the output without that light gray background. Right, so there we go. All right, so that would wrap up this. So we have seen right, a little bit of kind of how our markdown file works. We have also made a contingency table, right, using some kind of basic probability knowledge. We've also calculated some expected values, and we have finally also used Bayes' rule, right, to create this updated beliefs based on gathering new data. All right, so I think that that is a good place to stop here. So this is Prof E signing off.